Hey there and welcome. Today we are going to dive into one of engineering's absolute coolest tricks. We're talking about how you can take a huge, complicated, spread out force and boil it down to just one single manageable point. This, my friends, is the magic of understanding distributed loads.
All right, to get our heads around this, let's start with a classic thought experiment. I want you to picture it, you just chilling out, perfectly comfortable, lying on a bed of thousands of super sharp nails. Yeah, sounds pretty crazy, right? So how in the world is that even possible? I mean, it's not some kind of magic trick. It's pure physics. And the secret? Well, it's all about how your weight, that force pushing down, is spread out. And that gets us to the core idea here, a distributed load. See, instead of one single point taking all that pressure, the force of your body is shared across hundreds, even thousands of nails. Each individual nail only has to support a tiny little bit of your weight, so no single point has enough force to break your skin. You've successfully distributed the load. Okay, so this isn't just for circus acts. This concept is, and I mean this literally, everywhere in the world of engineering. Let's look at some much bigger examples. I want you to think about the constant, massive force of wind pushing against a skyscraper, or the incredible pressure of a lake pushing against a dam. Heck, even a heavy layer of snow on your roof, or a pile of materials on a factory floor, those are all perfect examples of distributed loads. Now, engineers can't just say, oh, there's a lot of wind. They have to be super precise, right? So they measure the intensity of these forces, how much force is being applied over a specific length or area, using units like newtons per meter or pounds per foot. So we've got these huge, continuous forces all over the place. How on earth does an engineer actually work with that? Well, this is where the real genius, the real shortcut, comes into play. I mean, just try to imagine calculating the force of the wind on every single square inch or square millimeter of a giant building. You can't. It's an impossible task. You'd be doing an infinite number of calculations forever. And to solve this impossible problem, engineers came up with a brilliant idea, the resultant force. It's a single, make-believe force that perfectly represents the total effect of that entire, messy, distributed load. And this slide just shows it perfectly. On the left, you've got the messy reality, all those little arrows pushing down everywhere. But on the right, you have the engineer's elegant simplification. One clean, simple arrow that does the exact same job. It is a total game changer. So the million-dollar question is, how do you find this magical resultant force? It sounds complicated, but it's actually way simpler than you'd think. You just need to answer two basic questions. How much force is there, and where exactly is it pushing? Yep, we can break this whole thing down into two straightforward steps. First, we figure out its size, the magnitude, that's the how much, and then we pinpoint its location, the where. Let's start with magnitude, the how much. All you have to do is find the total area of the shape that the load makes on a diagram. If the load is spread out evenly, for example, it just makes a rectangle. So the magnitude is, you guessed it, the area of that rectangle. And what about the where? Well, that resultant force always acts through the geometric center of that shape. Engineers have a fancy word for this. They call it the centroid. But really, you can just think of it as the shape's perfect balance point. So let's look at the easiest possible example, a rectangular load. This is like having a pile of bricks spread perfectly evenly across a board. The magnitude? Easy. It's just the base times the height. And the location, what we call x-bar, it's right smack in the middle. Simple as that. Okay, but what if the load isn't even, like water pressure, which gets stronger the deeper you go? Well, that creates a triangular load. The magnitude is just the area of a triangle, 1/2 times base times height. And the location, the centroid, it's always 1/3 of the way over from the tall side. See? The same simple principles work no matter the shape. Okay, so we have this really clever way to simplify things. But why is this so important? Why is this more than just a neat math trick? Why is it absolutely critical for basically all of modern engineering? Let's just quickly recap. We started out with what was, for all practical purposes, an unsolvable problem. You had a structure with a potentially infinite number of tiny forces acting on it, and by finding this one resultant force, we've turned that infinite mess into a basic, solvable problem with a single, predictable force. And this is the key takeaway. This simplification is what makes structural analysis possible in the first place.
This one little shortcut unlocks everything else. It's what allows engineers to use their fundamental equations. It's what helps them figure out exactly how strong the supports of a bridge need to be. And ultimately, it's what ensures the buildings we live in and the dams that protect us are safe and stable.
This quote really just sums it all up, doesn't it? This single idea, replacing something incredibly complex with something beautifully simple, is the absolute foundation of making sure structures don't fall down. It turns chaos into predictable order.
And that kind of leaves us with a fascinating thought, right? If one simple arrow can represent the entire force of the wind on a massive sign, what other incredibly complex forces in our world, maybe even outside of engineering, are just waiting for us to find their simpler explanation? What other big, messy problems could be solved if we could just find their resultant force?